Hello everyone, and welcome to this video tutorial. This video is devoted to the practical aspects of working with macroeconomic statistics. In particular, we will discuss the different types of data that you might encounter and put a special emphasis on working with economic time series data. We will discuss the properties of time series and the ways to manipulate them. Because economic decisions have to be made very frequently, we will focus on analyzing intra-year data collected at monthly or quarterly frequency. A lot of attention will be devoted to economic indices, one of the most common ways of describing the economic reality. Finally, we'll cover different types of growth rates and see which of them are most suitable for analyzing short-run economic developments and which ones are not recommended to use. First of all, let's consider broadly what kinds of data one usually encounters in macroeconomics. Empirical data is usually categorized into one of the three groups: cross-sectional, time series, and panel data. This classification is widely used in econometrics and applied statistics. It is also quite common in other fields, including sociology and psychology, although some variations in the terms do sometimes appear. These three kinds of data are distinguished by the number of objects and time periods that the data contains. Cross-sectional data contains information on a multitude of objects, such as individuals, companies, or countries, at a particular point in time. Time series data, on the contrary, follows a single object over a number of periods. Panel data can be viewed as a combination of the two previous types. Many individuals are followed over a number of periods. Keep in mind that when talking about panel data in economics, we usually mean that the same objects are observed in each period. If this is not the case, then such data is called repeated cross-sectional data. Macroeconomists are mostly interested in the time series studies, that is, tracking the development of particular economic variables over time. However, economists interested in cross-country growth and income differences often work with cross-sectional and panel data as well. Recently, macroeconomic research started to incorporate panel microdata, describing the behavior of households and individual firms. This allows to study not only the aggregate economic dynamics, but also the distributional effects of various macroeconomic policies. Here you can see an example of how cross-sectional data may look like. Here we have only one single period, t equal to 1. At this period, we collected information on k different characteristics for n different individuals. Examples of such data may include age, sex, city of birth, and final grades of 150 ICEF students in 2024, data on income and expenditures on different kinds of goods and services of a sample of Russian households in a particular year, or revenue, assets, tax payments, and profits for 400 public companies in 2023. Research questions, which can be answered by using cross-sectional data, vary a lot. On the slide, you can see one example of a statement or a hypothesis that can be checked with cross-sectional data. It is usually something along the lines of, in a particular period, individuals with a value of x higher by 1 unit were associated with having a value of y higher by beta units, all else equal. An example of this would be a study based on the Household Income Survey conducted in 2023. Using cross-sectional data on income and personal characteristics of different individuals, we could conclude that ceteris paribus, income tends to be 15% higher for households where there is at least one university graduate. The ceteris paribus condition in interpretation, which means all else equal, is the key term. Without it, the interpretation becomes incorrect. Time series data is probably the most widespread when it comes to macroeconomics. It contains observations which track one individual over t consecutive periods. Examples of such data include stock prices, GDP, and inflation for a particular country, etc. Time series data can be used to make conclusions regarding the dynamic impact of one variable on the other. For example, after studying Russian macroeconomic data, we could conclude that a 100 basis point increase in the policy rate of the Bank of Russia was associated with a 0.7 percentage point decrease in inflation over a 1-year period. This is the kind of statement that we usually make when analyzing time series. Panel data is basically a combination of the two other types of data. It includes cross-sections describing the same individuals at different points in time. Examples of panel datasets include a collection of macroeconomic statistics for a group of countries, data from financial statements of a number of companies, and surveys that repeatedly monitor the same households over the years. Panel data analysis allows to identify the relationships between economic variables with a much higher precision. Because when analyzing panels, we essentially average across a number of individuals, the impact of their unobserved individual characteristics is essentially factored out from the analysis. Panel data is also useful when studying heterogeneity, that is, the uneven response of individuals with different characteristics to the same economic shocks. In what follows, we will focus on economic time series and their properties, leaving the discussion of cross-sectional and panel data out of the scope of this lecture. Now, let's restate again what a time series is. A time series is an ordered set of observations relating to one or several characteristics of an object. Depending on the number of variables, a time series can be univariate, containing data on just one variable, or multivariate, meaning containing data on a lot of variables. Most often, a particular value that a time series takes is called a level. This is done to distinguish the original values of a variable from their transformations. For instance, if we have observations of Russian GDP over time, we will call this Russian GDP series in levels. If we then decide, for some reason, to analyze the logarithms of GDP, we will then talk about the log levels. As you know, all economic variables can be classified as either stock or flow variables. Stock variables represent a measurement of some phenomenon at a particular moment in time, at the end of the month, on January the 1st, etc. A time series containing values of a stock variable is called a momentary time series. Flow variables, on the other hand, describe a phenomenon over some period of time, a month, a quarter, a year. In this case, the corresponding time series is called an interval time series. Regardless of their type, time series can be collected at different frequencies. Most of them are either monthly, quarterly, or yearly. For instance, the Consumer Price Index is a stock variable calculated and published monthly. GDP, on the other hand, is a flow variable with a quarterly frequency of publications. Since economic activity is not uniform in different periods, time series are usually said to have a dynamic structure. This means that any time series can be decomposed into a number of subcomponents. Generally, 3 of them are distinguished: the calendar and seasonal component, the trend and cyclical component, and the irregular one. We will come back to the meaning of each component in a couple of slides. As you well know, the variables describing economic activity can be presented in nominal or real terms. Nominal variables are expressed in current prices, that is, the prices that were actually in place during the measurement period. The dynamics of nominal variables reflects both price and quantity movements. That is why, in general, they are not comparable across different periods and cannot be analyzed meaningfully. Still, in some cases, the relationship between nominal variables can be of interest itself. Real variables, on the other hand, are free of the impact of price changes. They are expressed in constant or base period prices and only reflect the changes of actual physical quantities of goods and services. Keep in mind that different periods can be selected as base periods. What is more, it is very common for statistical agencies to change base periods from time to time. That is why it is always necessary to check whether variables are expressed in the same prices before proceeding to analyze them. For example, the comparison of GDP values expressed in 2011 and 2021 rubles is obviously meaningless. The established convention in Russian public policy is to analyze government budget statistics in nominal terms only. While it is true that finding a suitable deflator to convert them to real terms is not quite easy, the analysis of nominal variables might be misleading. For example, a claimed 5% increase in education spending can in fact mean that the government spends less on education in real terms if inflation is high enough. Let us focus on the frequency of various economic time series and discuss how to work with different kinds of intra-year variables. Previously, we've already mentioned that economic statistics is published at different frequencies. This basically follows from the fact that some variables can be very easily calculated frequently, on a monthly basis for instance, while others require collecting and processing tremendous amounts of raw statistical data. Obviously, yearly macroeconomic statistics is the most accurate type of data. It is compiled using detailed statements of all kinds of enterprises working in the economy. Yearly data is very useful when analyzing long-term trends and making cross-country comparisons. However, day-to-day decision-making cannot rely on yearly macro statistics. Take the job of a central banker as an example. The Monetary Policy Committee meets more than 10 times a year, and during each meeting, a decision which directly impacts economic activity has to be made. To make these decisions, policymakers use intra-year data with minimal publication delays. By construction, these variables have much lower precision and can be revised later. Still, they enter the policymaker's information set and contain valuable data about economic activity. Intra-year macroeconomic data often appears in the news and in public discussions. However, many conventional ways of interpreting such data are bluntly incorrect, which may lead to spurious conclusions. And we'll talk about that in the last part of the lecture. This slide shows the timeline which the Russian Statistical Agency follows when publishing yearly GDP estimates. Earlier we've said that yearly data is usually more accurate. However, here you can see that in fact it takes 5 revisions and almost 2 years to arrive at the final estimate of economic activity for a given period. Clearly, such a timeline is of little help for analyzing what is actually happening in the economy at this very moment. In contrast, quarterly GDP statistics appears much faster. Take the first quarter of 2023 as an example. According to this timeline, it takes Россtat only 1.5 months to calculate an initial estimate of GDP for that quarter. As additional statistical data arrives, this estimate is gradually revised. Usually, it is the second estimate that is accurate enough for further analysis. Here you can actually see how quarterly GDP is revised in different countries. In most cases, except for the US and Germany, initial estimates tend to be conservative, meaning that as the time passes, they are revised upwards. Data analysis shows that 3 years after the initial publication, GDP growth is revised by 0.36 percentage points in Russia and by 0.2 percentage points in OECD countries. This slide demonstrates the extent of revisions for other important macroeconomic variables in Russia, which are monthly or quarterly. Retail trade figures, for example, are revised upwards by almost 1% after the publication. Real wage, on average, stays the same, although the median and the absolute revision are non-zero. Inflation, on the other hand, is never revised. The presence of revisions does not necessarily mean that the data is falsified. Such claims usually appear because journalists and even some analysts are unaware that the revisions are actually part of the official published statistical methodology. Of course, on average, the extent of revisions should converge to zero. If initial estimates are systematically biased upwards or downwards, this might reflect a methodological deficiency. Obviously, larger revisions can be expected in times of economic turbulence. This happens because initially published first flash estimates often rely on econometric and interpolation techniques. They do not tend to perform well when economic conditions are changing very fast. Lastly, if the reasons for revisions are left unexplained and there is a systematic bias in either direction, it can be the case that the data is altered to show the necessary outcome. This is much more likely for politically sensitive variables, such as the GDP or real income statistics. Sometimes very extensive research is necessary to actually uncover such manipulations. Now we have seen that the data can be collected at various frequencies, depending on the methodology and the available resources. However, when analyzing economic performance or building an empirical model, one usually needs to have variables of the same frequency at hand. Generally, there exist two types of solutions to this problem. One way is to interpolate low-frequency variables to a higher frequency. This approach requires finding a proxy for the variable of interest which is available at higher frequency. For example, quarterly GDP data can be interpolated to monthly frequency by using industrial production and retail trade dynamics, which are published monthly. However, this approach is highly sensitive to the choice of reference variables and has to be applied with caution. In practice, much more frequently, the higher frequency variables are collapsed to a lower frequency instead. This method is much easier to implement and it does not depend on the researcher's discretion, but it inevitably leads to information loss. In what follows, we will cover the second method in more detail. In fact, the proper way depends on the nature of the underlying variable. First, we focus on flow variables. Recall from earlier that these variables measure economic activity over some period. To convert such variables to a yearly frequency, one can do one of the two things. You can either sum up or average the values of the variable for a particular calendar year. For example, to get the yearly volume of retail trade based on monthly statistics, it is necessary to find a sum of 12 consecutive monthly values. Alternatively, one could average them out, although this is not often used in practice. When doing these operations, it is necessary to keep in mind that there is a distinction between nominal and real variables. Summation or averaging of nominal variables is in general incorrect because it requires us making an operation with incomparable figures. That is why before this type of conversion, they have to be transformed into real terms. When it comes to stock variables, the story is slightly different. These variables measure a continuous economic phenomenon at a particular point in time. For example, the central bank and commercial banks every day contribute to creating and destroying money in the economy. The measure of money supply represents the result of these actions up to a particular moment. That is why it makes no sense to sum up these values. Instead, to convert monthly stock variables to yearly, one has to just take the measurement made at the end of each respective year, for example on December 31st. Alternatively, the average can be calculated. Keep in mind that these two operations have different interpretations. In the first case, it will be the end of year value of money stock, while in the second year, it's the average money stock in the whole economy over the whole year. Since now we know how to operate variables of different frequencies, it is time to discuss the dynamic structure of economic time series. For analytical purposes, using the raw time series in levels is most often insufficient. Intra-year statistical data is usually used to identify changes in short-term trends. In other words, we need to answer whether the economic downfall has ended or has the tight monetary policy been able to bring down inflation. To answer these questions, economists try to decompose the observed time series into several structural components. The calendar component reflects the variation in economic activity related to different number of working days, holidays, etc. The seasonal component describes regular variations related to weather, consumer habits, and the production cycle that happen within 1 year. It is important to understand that seasonality, by definition, cannot be discovered in time series which are measured at yearly or greater frequencies. The irregular component represents random fluctuations in reported economic activity, which can be related to one-off shocks and data manipulation or reporting mistakes. The most important component is obviously the trend and cyclical component. It contains the most valuable information about ongoing economic activity. To decompose the series into these components, econometric techniques and models have to be used. Naturally, there is no single right or wrong way of doing so. The methods here might range from fitting a simple linear trend to building a complex structural model with unobserved components. Evidently, most often, we are not interested in seasonal or calendar variations in economic activity. Imagine that the central bank knows that consumer demand always increases before Christmas holidays. This fact merely reflects regular consumer habits which are not related to the current state of the business cycle. That is why seasonal and calendar variability has to be removed before meaningful analysis can be performed. Most frequently, this is done by using special econometric packages and programs called X13 ARIMA or SEATS. They are available standalone and as well as in R, Python, and eViews. This slide shows the difference between raw and seasonally adjusted quarterly real GDP in Russia. Here you can clearly see how difficult it is to draw any kind of conclusions based on raw data. In the presence of seasonality, this is essentially impossible because the variation is very strong. Obviously, neighboring values of the raw time series cannot be compared to each other because the number of working days in the first and in the second quarter do not coincide. The next important subtopic concerns various transformations that can be performed over the time series. Obviously, since algebraically a time series is essentially a vector, one can perform any kind of algebraic transformations over its elements. For instance, the levels of a time series can be normalized, which means divided by the same constant, or taken to a particular power. One of the most widely used operations in economics is the logarithmic transformation of a time series. This is a monotonic transformation with a number of very nice properties. Firstly, taking the log allows us to greatly reduce the variance of the time series and make values better comparable to each other. Secondly, most economic variables grow at more or less constant rates over time. This means that the dynamics of their levels exhibits exponential growth. The log essentially kills the exponent and transforms the exponential trend into a linear one. Consequently, the slope of the log level of a time series on the graph is equal to its growth rate. Keep in mind that the log transformation is applicable for time series which can never take zero or negative values. The log level form of a time series is sometimes one of the best ways to visualize the data. To see this, compare the following three graphs. Here we plot the dynamics of the ruble exchange rate to the US dollar in levels. Judging from the graph, it seems that in the 21st century, the exchange rate was much more volatile than previously in year 2000 or before. The second graph shows the decimal log of the same exchange rate. Pay attention to the vertical axis. Instead of incremental changes, it now reflects proportional changes. This means that between this point and this point, the exchange rate depreciated by a factor of 10 and not just by 10 units. The final graph shows the natural log of the ruble exchange rate. Essentially, it's very similar to the previous one, apart from the figures on the scale. As you can see, visualizing the exchange rate in levels was misleading. The first graph makes it seem that most of the volatility happened in the 21st century, even though in the 90s, ruble depreciated by a factor of 47. It is useful to note that the decimal log is much more suitable for visualizations because the powers of 10 are easily interpreted. However, for analytical purposes and fitting econometric models, we usually stick to the natural log because of its unique relation to the exponent. That is why, in what follows, we will talk about the natural log. Sometimes, instead of representing the time series in log levels, it is often useful to transform it into log difference form. This means that we take the difference between the logs of neighboring time series values for each period. To facilitate interpretation, we also multiply by 100. For relatively small changes in the levels of the time series, log differences approximate percentage changes. This results from the first-order Taylor expansion of the log difference around the point xt over xt minus 1 equal to 1. First, recall that a Taylor expansion of any function at point x0 is equal to its value at point x0 plus its derivative evaluated at this point times x minus x0. Applying this to the natural log, we get that it is equal to log 1 plus the derivative of the log at point 1 times x minus 1. After some trivial transformations, it's clear that this is equal to just x minus 1. Now do the same for the log difference of the time series. Log xt minus log xt minus 1 by the properties of the natural log is equal to the log of their quotient. Using the Taylor expansion that we've just derived, we get that it is approximately equal to 100 times xt over xt minus 1 minus 1. If you take a closer look at this expression, this is exactly the percentage growth rate of x between the two periods. Compared to percentage changes, log differences are symmetric. This means that if a variable changes its value and after several periods returns to the initial one, the sum of log differences will be equal to 0. This is not true for ordinary percentage changes. Consider a simple example of some country where for 3 years GDP was equal to 5, 6, and $5 trillion. If you calculate percentage changes in the second and the third year, we will get plus 20% and minus 16%. Even though the GDP returned to its initial level of $5 trillion, the sum of percentage changes is obviously not equal to 0. In contrast, log differences are equal to plus 18.2 and minus 18.2 in both cases, and obviously this sums up to 0. This property is the actual reason why most econometric models use log differences instead of percentage growth rates. This graph shows the relationship between percentage changes on the horizontal axis and the logarithmic changes on the vertical axis. You can see that for relatively small changes, they are very close to each other, almost equal. Only when the percentage changes start to exceed 20, somewhere over here, can we see the difference. The difference between them is the approximation error resulting from the first-order Taylor expansion that we did. Let us now turn to the discussion of one very popular way of presenting economic data, namely creating economic indices. Economic activity is a very complex phenomenon. At the same time, the economy produces millions of goods and services, all measured in different units. In some cases, the data on these different products is commensurable. For example, if we know the amount of cast iron that was produced by all plants in the country, we can just find the sum of production and compare with what was produced in the previous month. However, this is not always possible. One cannot just find a sum of milk, iron, and car production because their volumes are directly incommensurable. The thing is that macroeconomics is interested in aggregates, which consist mostly of incommensurable moments. The price level, economic activity, industrial production, all of them contain phenomena which are measured in different units. One way of tackling this problem would be to analyze each market separately. However, given the tremendous amount of different markets in the economy, this is hardly manageable. What is more important, the object of interest is the aggregate dynamics, which is hard to guess by looking at 1,000 individual markets for different products. This is why economists create economic indices. An index is by definition a relative measure. We can construct an elementary index by normalizing the levels of a time series by its value in a particular period. This period is called the base period. The resulting index is, by extension, called a fixed base index. Such an index describes the dynamics of a variable in relation to the base period t. The fixed base index is the primary form of data which can be used to obtain many others. Consider the example of steel production volumes over 4 periods. Suppose we choose the first period as the base of comparison. To create an elementary index, we need to divide each value of the time series by the value in the first period. So 300 by 300 is equal to 1, 500 by 300 is equal to 1.66, etc. The resulting time series is obviously unit-free, so it doesn't have any kind of scale. And this is our elementary fixed base index of steel production. Elementary indices are usually aggregated into composite indices. The particular way to do this is very different in each case. For example, when calculating the consumer price index, the elementary price indices are weighted using the share of consumer spending on these goods. So the more people spend on a particular product, the more weight the CPI attributes to this product. With the industrial production, the value added is used as a weight. Now consider a hypothetical economy which produces only milk and steel, just 2 products. Let's assume that the value added in the milk industry is equal to 25% of the total value added in the economy, and the rest is attributed to the steel industry. This is how we construct weights for our industrial production index. For this economy, we also have 2 elementary indices, which reflect the production volumes of milk and steel compared to the first period. To obtain a composite index, we just multiply the value of an index by respective weight in each period and sum them up. For instance, in period 2, 0.75 is multiplied by the weight 0.25 plus 1.66 multiplied by the weight 0.75. The result is 143. The resulting series is the composite industrial production index for this economy, It allows to track aggregate economic activity in the industrial sector without having to resort to the analysis of each particular market. Obviously, the more goods there are in the economy, the more significant is the importance of building an industrial production index. This graph shows two price indices for the Russian economy: the consumer price index, the CPI, and the producer price index, the PPI. In both cases, we have the fixed base index with the base period in January 2020, right here. You can see that the index value is equal to 1 or 100%. When the base period is the same, the dynamics of the two indices is comparable. We can see that over 4 years, consumer prices increased by a smaller amount than producer prices. We also observe a much greater volatility of the producer price index. The smoothness of the CPI reflects the incomplete or delayed pass-through from producer to consumer prices. There is also actually another factor which contributes to the differences, the systematic differences between these indices in Russia. The PPI in Russia includes prices for exported raw materials, oil, gas, and metals, which are known to be very volatile because they are determined outside of the economy in the global market. Obviously, these goods are not included in the consumer basket, and that's why the distinction between how the PPI and the CPI behave. The final part of the presentation concerns various types of growth rates, which are typically published by statistical agencies. We will discuss the relative merits of each type of growth rate and suggest the optimal way of analyzing intra-year economic dynamics. The first type of growth rates is period-over-period growth rates. In statistics, they are also called chain indices. They are calculated by relating the value of the time series in period t to the immediately preceding value at period t-1. That is why, in colloquial usage, they are designated as MOM or Q over Q growth rates, meaning month-over-month growth or quarter-over-quarter growth. The chain index is called this way because in each case the value is compared to the immediately preceding one. If we multiply or chain such growth rates together, we will be able to restore the original fixed base index up to a normalizing constant, so the value of the first period might get lost. However, this is not of significant importance. Suppose that in February, March, and April, the month-over-month growth rate of consumer prices was equal to 10%, 10%, and 5%. So this is the first month, January, this is February, this is March, and April. So, knowing these growth rates, what can be done to obtain a fixed base index? If we take January as the base of comparison, then we can do the following. So, in January, the fixed base index is equal to 1. In February, it's equal to 1 times the growth, which is 10%, so equal to 1.1. In March, it's 1.1, the previous value, times 1.1, which is 121. And finally, in April, it's 121 times 1.05, which is equal to 12705. So this is the way for us to transfer between those two data types. When we have the base index, we can always calculate growth rates, and having the growth rates, we can restore the dynamics of the fixed base index, only up to the normalizing constant. So the value in January could be actually any value, 1, 100, 300, it doesn't matter. Here we see a graph which shows the evolution of a fixed base index. The chain index, or the month-over-month growth rate in period 11, can be calculated as x11 over x in period 10. So this is basically ordinary percentage change. This graph compares the dynamics of a fixed base and chain CPI indices in Russia. Obviously, the second one allows us to see incremental changes from one period to the other, while the first one only shows us the cumulative change from the base period. The advantage of chain indices is obvious. They are mathematically equivalent to the first derivative of a function, which shows its growth rate. Visually, they are much easier to analyze than fixed base indices. However, month-over-month and quarter-over-quarter growth rates tend to be very volatile and noisy, especially when strong seasonal and calendar effects are present. Again, because of seasonality, we cannot really compare adjacent values of chain indices to each other. As discussed earlier, before any meaningful analysis, seasonal adjustment has to be made. This graph compares the original and seasonally adjusted inflation rate calculated as the monthly change in CPI in Russia. You can clearly see that the dynamics are quite similar, although the adjusted series is slightly less volatile. You can see that the local minima of the unadjusted series, like this, and this, are actually just seasonal effects. It turns out that they are related to fruits and vegetables becoming cheaper during the summer. The adjusted inflation rate allows to get rid of such variations, which do not reflect any variation in actual economic activity level. Even after seasonal adjustment, interpreting chain index values is quite hard. Take a monthly increase in prices by 0.4% with seasonal adjustment. Can we say that this is a lot or not? How does this align with the objective of the central bank? To answer this question, economists calculate seasonally adjusted annual growth rates. The SAAR shows how the value of the variable would change over one whole year if it continued to change at the same rate as today. To calculate seasonally adjusted annual rates, we need to perform three steps. Firstly, do the seasonal adjustment of the fixed base index. Secondly, calculate period-over-period growth rates, as discussed earlier. Thirdly, these growth rates have to be raised to the power of 12 or to the power of 4, depending on the frequency of the data, monthly or quarterly. For example, if in November prices increased by 0.84% compared to October, then the seasonally adjusted annual rate of inflation is equal to 1.0084, which is exactly 0.84%, to the 12th power minus 1, that is 10.56%. It means that if prices continue to grow that fast as in the current month, inflation would actually reach more than 10% over a year, which is quite a lot compared to the inflation target of the Russian Central Bank. Obviously, seasonally adjusted annual rates can be transformed back to the original form. For instance, the 5.7% SAAR growth means that an increase in GDP quarter over quarter was equal to 1.057 to the power of 0.25 minus 1, which is 1.4%. But if GDP continued to grow at this rate over the next 3 quarters, then the growth would be equal to 5.7%, which is exactly what the seasonally adjusted annual rate showed us. The graphical interpretation of the SAAR growth rate is quite straightforward. It shows where the variable would be if it was to grow at the current rate for the following 12 months. Since we assume a constant growth rate over this period, you can actually see that the trajectory is not linear, it's exponential, which reflects compounding growth. This graph shows SAAR inflation in Russia compared to the Bank of Russia's inflation target of 4%. We can easily spot the periods where inflation was mostly on target, somewhere around here, and the periods of elevated inflation, as in 2014-16, 2023, and the beginning of 2022. Seasonally adjusted annual rates allow to identify economic trends quite fast, but this comes at a cost. The previous graph clearly shows that they are very volatile. Sometimes, to get rid of this excess volatility, we take moving averages of these growth rates. A moving average means replacing each value of a time series with the average of several neighboring values. Most often, a 3-month moving average is used, meaning that at each point in time, we take the average of the current growth rate, the growth rate in period t-1, and in period t-2. Judging by this graphical exposition, you can see that a moving average is clearly less noisy and often is a better way to visualize data. One of the most common indicators in economics is the year-over-year growth rate. For yearly data, there's no problem with this indicator. You just take the value of it in 2 different years and compare. There's nothing wrong with that. However, there are some difficulties with using the same indicator for intra-year data. It is calculated as the ratio of the value today and the value 12 or 4 periods ago, depending on the frequency, monthly or quarterly. Usually, such a transformation is performed to get rid of seasonality. However, this turns out to be quite a poor way of analyzing economic statistics. First of all, residual seasonality may still be left, because seasonal patterns evolve over time. They are not constant. That's why by dividing the values over the same months, you can still have some residual seasonal effects. The second and the major disadvantage is that year-over-year growth rates cannot be chained together to yield a fixed base index. This means that this transformation is associated with a serious loss of information. As we will see quite shortly, year-over-year growth rates also respond to current economic conditions with a significant lag. This lag is of 6 months, which is unacceptable when swift decisions have to be made. Finally, the interpretation of these growth rates is complicated by the presence of the base effect. The base effect actually means that when year-over-year growth is greater than 1 or 100%, it doesn't actually mean that the variable is currently growing. It merely means that its value increased compared to what was happening a year ago, and a whole lot of things could have happened 1 year ago. This point is well illustrated on this graph. The year-over-year growth rate in period 22 is calculated as the ratio of x22 over x10. This growth rate is going to be positive, obviously, because x22 is greater than x10. However, we can clearly see that for a number of periods leading to point B, the variable was actually falling. So, using the year-over-year growth rate does not allow us to determine this fact, and that's where the delay comes from. The delayed response of year-over-year growth rates is clear once we compare them to seasonally adjusted annual rates. You can see that the local maxima and minima of the red line are usually shifted to a period of exactly half a year into the future. This is the primary reason why central banks rely on SAAR rates instead of year-over-year ones. Imagine if key rate decisions were made with a 6-month lag. The central bank, in this case, would actually fail in its main stabilizing function. The final type of growth rate is the cumulative year-over-year growth rate. This is encountered almost exclusively in Russian statistics as well as in some countries of the former Soviet Union. This calculation reflects the average percentage change in the variable since the beginning of the year compared to the same period a year ago. This operation should not be used at all when working with economic statistics, because it involves a very serious loss of information and does not allow us to restore the fixed base index. Even for adjacent months, such growth rates are completely incomparable. This happens because they are measured over different time intervals. Finally, cumulative year-over-year growth rates completely distort the dynamics of the series. Unfortunately, very important macroeconomic variables are published by Rosstat only in this form, which prevents any further meaningful analysis. Graphically, calculating cumulative year-over-year growth rates is equivalent to finding the ratio of the sum of values in the purple segment to the sum of values in the blue one. Here you can compare the seasonally adjusted annual rates of inflation with the cumulative year-over-year growth of consumer prices. It is clear that the red function, the red line, exhibits very strange behavior, which does not reflect current inflation dynamics at all. Between December and January, the value has very abrupt changes, which are not present in the original data. Obviously, using and interpreting this kind of data should be completely avoided. The final note that we will make is related to the potential sources of discrepancy between different kinds of growth rates and economic indicators in general. As discussed above, all types of growth rates can be derived from the fixed base index. However, if the underlying indices are built using different methodology, growth rates cannot be compared. For example, in Russia, Rosstat publishes flash CPI estimates every week. However, if we calculate the change in prices over 4 weeks of the same month and cumulate this change, it will not be equal to the actual inflation rate for this very same month. The reason for this is actually simple. Weekly inflation is calculated using a reduced consumption basket, which is almost 5 times smaller than the case of the monthly observations. The second example is the real wage statistics. To determine changes in real wages, Rosstat compares wages across a comparable sample of enterprises. So, when calculating month-over-month growth in wages, they compare companies which exist in this month and existed a month ago and see what was the dynamics of the real wage between them. When calculating year-over-year growth rate in wages, companies which exist now and existed a year ago are compared. Obviously, the samples need not be the same. That means that monthly growth rates will not add up to yearly ones. To illustrate the point, we do the following exercise. First, we collect month-over-month growth rates of real wages. Then we chain them together, as we discussed previously, to obtain a fixed base real wage index in Russian economy. Based on this fixed base index, we calculate year-over-year growth rates. These calculated growth rates are plotted as the red line in the graph. We then compare these growth rates to those rates that Rosstat published by itself. As you can see, they are not equal. The officially published estimates overstate real wage growth, especially in 2022 and 23. The reason for this is simple. As you probably know, in 2022 and 23, Russian economy faced a considerable deficit of workers in the labor market. In this case, companies compete for scarce workers by bidding up their wage offers. Less efficient companies who cannot survive the wage race just exit the market. Basically, this means that when calculating year-over-year growth rates, Rosstat only compares wages paid by surviving companies. By definition, these companies survived the competition because they were able to pay higher wages and attract more qualified workers. That is a perfect example when a small methodological difference results in sizable differences in the resulting figures. This doesn't actually mean that the Rosstat year-over-year growth rate series is wrong. This just means that it has to be interpreted with care, considering the methodology that is behind it. This is basically the main message of this lecture. Today, you have seen how various economic indicators are derived and what they can actually mean. In the data-rich environment, where there is almost always too much information available, it is critical that before trying to interpret some statistics or build a model, you take a moment to reflect on what the data actually means. This often helps to prevent comparing the incomparable and interpreting what cannot be interpreted. Hopefully, this lecture will serve as a useful guide in case you need to perform a macroeconomic case analysis for a particular country. Thank you for your attention and see you in the next tutorials.